Okay, everybody, couple more little topics on this electron configuration stuff, and then we're good to go. So, my question to you is: are you excited? All right, are you excited? So, how can we take the ground state, excited state, when we talk about an electrons moving around when they add energy to the atom? How do we do this with electron configuration? So that's really the next step. So, just a couple things along the way. Remember what an excited state and ground state is. Okay, ground state is when the electrons are in their lowest energy orbitals, right? So an unexcited atom has electrons that are most attracted to the nucleus and in all their boxes where they're going to be. Okay, everything written in the periodic table, okay, are going to be in the ground state. All right. So how do you show this in the excited state? Okay, so let's just think of let's just go to fluorine for a minute. Okay, and fluorine is atomic number 9. So it's going to have a 1s2, 2s2, 2p5 designation. Okay. So again, if you look at this, and again, if you look at your periodic table on your reference table, you may see this written in the box as a 2-7. Okay, the 2 meaning 2 is in the first energy level. Okay, and this is combined as a combined number. So the 5 and the 2 is a 7. So this would be the first energy level. This would be the second energy level. So sometimes you'll see it written as a 2-7, and that's the Regents version. Okay, in the honors version, in the regular version, we have this. Okay, anyway, so that would be in the ground state. Now, remember what's happening is in the excited state is you have the nucleus, and then you have electrons in levels are going around the nucleus. And if you have an electron here, remember what the excited state is. It goes up to another level. Now, it can go there or it can go there, right? So remember, it's how you're going to move up. Okay, so what we want to do to show that is to take electrons from some lower energies, from lower orbitals, and simply move them up to higher energy levels, and just write down what that would look like. All right, so again, there's so many different ways you can do this. I mean, there's really an unlimited or kind of an unending different possibilities you can do this. But I chose to do something like this. So if this is your ground state, a possible excited state might be keeping the 1s2, keeping the 2s2, but taking an electron out of the second p, or out of the p level, and then moving it up temporarily into the 5s1. Now, why do I choose 5s1? I don't know. I could have chosen 3s1. I could have used 4s1, but I happen to choose 5s1. So that's a possible excited state. Okay, another possible excited state. Maybe I can take the 1s2 and take one out of the 1s2. I can't put it in 2s2 because it's filled already, right? Because this would already have 2 electrons in it, so there's no place to put it. However, I can skip the 2p5 and leave it the way it is, right? Just like it was here, and then move it to 3s1. So again, that's another option. Okay, another option is I can take taking 1s2. Maybe I want to take one out of the 2s2 and move up to 4p1. So again, you can see there's just there's so many different ways you can do this. I mean, you probably can come up with some on your own. The idea is, moving electrons up. Okay, so if you wanted to write the little code for this, you could write, instead of 2-7, this would be 2, 6, and then 1, right? Or 2, 6, 0, 0, and 1, because you're moving it up to 5. So that would be first energy, second energy, third, fourth, and fifth. Okay, or if you did this here, this would be 1, 7, 1, right? Okay, or this would be 2, 6, 0, and 1. Okay, and what's the commonality here? The commonality is a couple of things, right? I never lost or gained electrons. I always left the electrons in the atom. I just moved them to a higher spot. Okay, so we got to watch a couple things. For number one, you can't overfill an orbital. So for example, if you have an S2, you cannot put anything else in it. So you can't have an S3, right? So you can't have that. Okay, and if you had a P6, right? So a P6 would be a 4P6, so 1, 2, 3, 4, 5, and 6. You can't put another electron in there because that would be, you can't have a P7, right? Because you can't overfill. So you can't overfill orbitals, the boxes, okay? And you can't add and subtract electrons. You can only move them to higher energy levels. Where you move them is entirely up to you, all right? So that's the kind of thing that we can do with ground excited state. So it's very easy. So let's just say I had to write an excited state for calcium atom. Well, I'm going to write it in the ground state. So the ground state for calcium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, And again, you want to confirm this with, the periodic table. Make sure you know what you're doing. 4s2. Okay, now let's just say I just wanted to, maybe write the shortcut for this, just because I feel like it, just to review here. So again, this would be the previous noble gas would be argon. So I can say argon. So really calcium is argon 4s2. All right, so that's just that. And now my excited state, I would simply say, and then this is up to me, right? It's up to you if you want to do this. I would say 4s1. Maybe I want to go to 5s1. Okay. So again, it's up to you how you want to do that in this. And again, ask in class if we can do another example, but I'm going to leave it with one example here. All right. All right. Last thing, and this is probably the most important thing. We're going to make this a little bit easier, believe it or not. Things are going to get easier here. And the key is something called a valence electron. And valence electrons are super, super, super important. In fact, this is the most important electrons you'll have in this unit. Okay, so first of all, what they are the outermost, and I use the word outermost, really important. The outermost energy level S and P electrons. Okay, and the transition metals are a little special because they can use the D electrons. Because remember, D electrons are very close to the S. Okay, as they begin to fill. So we've seen that before. And outermost. Now, why is outermost the most important? Well, outermost is important is because remember, if the nucleus is here and the outermost is there, that's going to be seen by another atom. That's going to be close to another atom. Okay, so that's important. Okay, now why is this the case? This is of supreme importance. Okay, these are the electrons that are involved in chemical bonding of elements. Okay, and are responsible for what that element is going to do for its chemical properties. So if we say that potassium hits water and it explodes, that's because of potassium's electron configuration. If we say that oxygen is a very reactive element because when you breathe it in, it really reacts with things in your body, it's because of the electron configuration of oxygen. Okay, so really important that you understand that. All right, elements with the same electron configuration, same electron structure, same valence electrons have very similar reactivity. They act very similar. In fact, they're in something called a chemical family. Okay, a column in the periodic table. Columns in the periodic table. Okay, columns in the periodic table have same valence electrons, equal valence. So it's really important to know that they have similar reactivity. Okay, so a couple of ways you can find the valence electrons in an atom. A few ways you can do this. Okay, number one, okay, is finding the group number. And the group number you'll see is the column number. Is the column number in the periodic table. Now, a little change to this. I know this is not like it's wrong, but it's a little misleading here, is that this should be 13, 14, 15, 16, 17, and 18, where the second number is the valence electrons. Okay, so 4, 5, 6, 7, and 8. So in column number, 1 valence electrons, 2, 13 would be 3, 14 would be 4, 15 would be 5, 16 would be 6, 17, and 18. Again, noble gases would have 8. Okay, number 2, it's the outermost S and P when you combine them. Okay, so really important. If you are let's just say you are 1, 2, okay, this is going to be 2p3, here's nitrogen. Okay, nitrogen would be atomic number 7. Okay, so nitrogen would be right here. Okay, if you take a look at this diagram, nitrogen is the P3 section. You would say the S and the P together would give you 5. Okay, so that's really important. And again, the other code for this would be, for nitrogen would be 2, 5, where that outside number is also the valence electrons. Okay, again, it would be 2 and then 5. Okay, that's the key. Okay, the simple configuration, which is this is the simple configuration. The simple config, okay, is also that last number. All right, so really important that you got that point. All right. All right. So again, 2, 5 is your valence electron number. All right. Now, a couple of things like how do we actually show the valence electrons? Okay, so now it's going to get a little even easier, and you got to be able to find them. So really important. So number one, we're going to take the outermost S and P. Okay, that's where you can find it. And what we're going to do is we can show this using something called a Lewis dot structure. I think some of you may have done this before. Sometimes we call it a Lewis structure or a dot structure or a Lewis dot structure or even a Lewis dot diagram or even a dot diagram or a Lewis diagram. It's different. It's known by a lot of different names, but I think we'll keep it with that. So basically what you do is literally show dots, like a dot represents an electron to represent just the valence electrons. Now, if you're not valence, okay, they call those core electrons. I did put this in the slide, but core electrons, or even sometimes they call them the kernel, Kernel. So kernel electrons and core electrons are the same one. So the kernel would, in this case, would be this. This would be the kernel. All right, this would be the valence. All right. So what we're going to do is, whoops, kind of messed up a little bit there. Okay. So what I'm going to do is I'm going to, if I go back a little bit, is I'm going to draw first. I'm going to draw the symbol for the element, and the symbol for the element represents the core electrons. Okay. And what I'm going to do is I'm going to put dots around this to represent the 5 valence electrons. So you can start anywhere you want. You can start at the top, or you can start on the side. However you want to do it. I'm going to start at the side, and I'm going to take my 5 valence electrons, and I'm just going to rotate them. I'm going to go 1, 2, 3, 4. And when I need to, now what I can do here is then double up. So I'm going to double up at 5. Okay? So the dot structure, or the Lewis dot structure of nitrogen, would have these 5 dots around the element. And that's the most important thing you want to know about this. Another way you could do this is you could start with the N. Okay, you could put 2 dots together to represent the S level, because remember, S is 2, and then fill in the 3 P's. 1, 2, 3, and that would be that. Okay, so that's the key. You want to go around in a circle and double up only when needed. All right. All right. So some period 2 elements. So we're in period 2, energy level 2. Okay, lithium. If I go back, if I take a look at this, lithium is a 2-1, so it's got 1 valence electrons, or 1s2, 2s1. There's my valence. I have 1 dot. Okay, beryllium's going to add 1 more to be a 2-2, so we're going to go beryllium here and beryllium there. Boron becomes a 2-3. I'm going to go 1, 2, and 3. Okay, carbon is going to be a 2-4. I'm going to go 1, 2, 3, 4. Okay, nitrogen is a 2-5. We did that before. It's 1, 2, 3, 4, 5. Kind of crazy that I went from all these long configurations to a bunch of dots, but that's what it comes down to. All right, because it's really
Can I please have Joshua
2-6,
Trevor to the main office? Joshua Trevor to
2,
the main office.
3, 4, 5, and 6. Again, we're doubling them up. Okay, and then fluorine 2-7. 1, 2, 3, 4, 5, 6, 7, and then you guessed it, 2-8. And again, 1s2, 2s2, 2p6. Remember, this is the valence, which makes the 8. 1, 2, 3, 4, 5, 6, 7, and 8. So no, everybody's paired up. So when everybody's paired up, you have a certain stability to this. Now, this is only the dot structures you could ever have, right? Because this is in period 1. I'm sorry, this is in column number 1. This is column number 18. And what we do is we start again. So if you look at the periodic table here, and we go to a different color, black maybe, all right, what we've done is we've gone from, lithium, which is here, over to neon here, right? We can fill these in: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. And where do we go next, right? We would start here at sodium, okay? But sodium, right, if you think about it like now, if you go 1 down, sodium would be 1s2, 2s2, 2p6, but now it's in the 3s column, right? Just like lithium was in the 1s column. So your valence is here, the outermost s, right? So that's going to be sodium. So sodium is going to have exactly the same dot structure as the element above it, okay? So you could even think, when you do this, that your elements in here will always be 1 dot. The elements in this column will always be 2 dots. The elements in this column will always have 3 dots, and so on. okay, as you go across. So really important. Once you got that, it's kind of easy because you're going to know how the elements react. So that would be dot structures. All right, so draw the dot structure for an element of sulfur. Okay, sulfur, if we take a look, sulfur is going to be in 6 here. It's in this section of 6. All right, so that's kind of easy to do. That's in the 3p4 range. Okay, so we're going to say Lewis structure. So sulfur is, if I put my right color here, yellow, sorry. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, 3p4 would be sulfur. So sulfur is atomic number 16. Right, so you have 10 here plus that. All right. Now again, if we want, I'm just going to review here. Let's just say we want to put this in a shortcut form. We could say neon, right? 3s2, 3p4. Now, don't make the mistake thinking that this is valence. It's the outermost SNP, which would be 6 valence, right? And again, if you wanted to double check, we can see that this is in group 16, which is here. All right, so it's 6 valence. We're going to take this guy. We're going to go 1. Again, you can start anywhere. You can start on the side or down or on the side, whatever you want. 1, 2, 3, 4, 5, and 6. Okay, and that would exactly have the same one as oxygen above it. Okay, so that would be an important thing there. Okay, how do the dot structures elements of the same group compare? They are identical. Because why? Because they have the same number of what? Valence electrons. Okay, and that is your key behind that. All right, so really, really important that you know how to do valence electrons. That should make things kind of easier for you. All right, and with that, we'll stop here and we'll move on to the next video. All right, bye.